Okay. I'm going to finish this set of presentations with a third presentation in which I'm going to speak overall. I'm going to speak of numerics. I promised you that I should say that which is the method, general terms, that we follow to make the computations. I would like to speak a little bit about this because I think that it is important to understand the ideas and overall to understand how can we get a good behavior at the time, at the final time. I have shown you some results in which the solution goes to 0 exponentially at capital T. And this is very, very, very interesting and very positive property from the numerical viewpoint. So how can we get this? And the answer, in short, the answer is using Kahneman, using the weights I have introduced. We don't forget the weights. I'm going to explain this now. Okay, a first simple example is this one. I have the very simple, the one-dimensional heat equation with the control on the right-hand side. X moves in an interval, 0, 1, and little omega is another interval, AB. And we try to find V such that Y at capital T is equal to 0, a null controllability problem. And we know that there exists V with this property. And this simple example has applications, heating, cooling, controlling a population, for example, in a river, something like this. It's interesting to solve this kind of problems, okay? Of course, what I am going to explain now can be done for more complicated problems, but in this case, it serves to give you an idea. This is the control that I am able to compute to make the solution reach exactly to 0. And you see that the control also goes to 0 exponentially. So it is relatively easy to compute and and also to use in the system. This is what I am able to compute, and I will tell you in a few moments how. And this is the state. The state starts at y naught is equal to the sinus of pi x. So this is very different from 0, and this time interval that is not too large, I'm able to make the solution go to 0. Okay. The second example is not so simple, rather more complicated. Navier-Stokes. In this case, we know that there is a local result. It was proved a lot of time by us. That says that if y naught is sufficiently small, it is possible to find V such that y capital T is equal to 0. This local result, because once you fix the time, you need small data. And as I have said before, it is open what happens if y naught is large. Nobody knows what happens for the moment. Nobody knows what happens if y naught is large. I insist that the problem is here. The problem is on the Dirichlet conditions that we are imposing here. If we change the boundary conditions, it is possible to do things. It was possible to prove a global result, but not in this case. Well, anyway, I am going, well, this is again a list of results, partial results that are possible to be deduced. All of them work very well, but not in the case in which Dirichlet conditions are imposed. This is the problem. I'm going to show an experiment, the results of an experiment in which we try to control exactly to this flow, with what is called Poiseuille flow. The Poiseuille flow is given by these values of y and p, the velocity field and the pressure. It is a stationary solution of the equation, and it is very well known. These are the iso values of this quantity of the first component, and this is the velocity field. I'm going to show you an experiment in which we are controlling the Navier-Stokes equation in a small domain in order to get a capital T, this target. This is the domain. The domain is especially two-dimensional. This is the base. X1 and X2 are this axis. And the vertical axis is, again, time. So this is the domain, the working domain, omega times 0t. And this is the control domain. I'm controlling only here, okay? And we start from this velocity field. This velocity field is clearly different from the Poiseuille flow, and we want to reach exactly to Poiseuille. Well, it is possible with the method that I am going to explain in a few moments. It is possible to solve this control problem. This is the initial state. This is the state at time approximately equal to 1. It is approaching Poiseuille flow, and well, the capital T was equal to 2 in this case. But just before capital T, we are already, in practice, we are very, very, very close to the Poiseuille flow. So it is possible to control exactly Navier-Stokes in this way. And the third example that I'm going to show you is even more interesting. It concerns exact controllability to what is called Taylor-Green flow. Taylor-Green flow is much more complicated than the Poiseuille flow. These are the isolines of the components of the velocity field, and this is the velocity field for Taylor-Green flow. It is not a stationary solution. It is a time-dependent solution. So in this case, we are trying to control exactly to a trajectory, not to a stationary solution. This is the domain in this case. Again, two-dimensional, two dimensions in the base and time in the vertical axis. And this is the control domain. What is marked with a dark zone is the control domain. And we start from something really very different from Taylor-Green flow. These are the isolines of the initial state. This is at time t equal to 0. At time equal to 0.6, something happens because we are controlling with a good method. This is time t equal to 0.9 before capital T. That was 1 in this case. We are already very approximately in the good situation. Of course, if we continue, we approach even more and we reach the good target. Okay, so it is possible to control these equations, and I'm going to show you why and how. Okay, this is the problem. The problem is to find V such that the solution to this equation satisfies. Well, for the moment, I'm going to look at the. In order to explain well the things, I'm going to show you what happens if we try just to approximate the final state at this level. So for the moment, I'm going to consider an approximate controllability problem, and I rewrite the controllability, the approximate controllability problem as the search of the minimal norm control in the sense of L2. That is the control that makes minimal this quantity, subject to this restriction, y a capital T, very small. epsilon very small. For the moment, I consider not the null contrariety problem, but the approximate contrariety problem that is written here. Well, as I have announced before, convex analysis says that this problem, that is a constrained convex minimization problem, can be rewritten as an unconstrained convex minimization problem that is here. That is obtained using a technique there are several names behind this technique: Fenchel, Rockefeller, Clan, Teman, etc. There is a technique that permits us to rewrite this problem equivalently like this one, in which the function to minimize is a little bit more complicated, but there is no restriction. So this is a problem in which the minimization is made with respect to phi t. Phi t is the final value of the adjoint system, and the adjoint system appears here in the functional to minimize. Okay, these two problems are equivalent, and people, in principle, have been tempted to try to solve this problem this way, trying to find phi t such that this quantity attains minimum. Okay? Unfortunately, this is the situation for small epsilon. If epsilon is small, and I recall you that epsilon is this quantity that measures the degree of exact controllability or non-exact controllability that we want. If epsilon is small, epsilon appears here, this is the solution in general. This is the kind of solution. I mean, you get a solution, a control, that oscillates near capital T. The reason is that this quantity with epsilon equal to 0 is not coercive. If you suppress this term, what you find here is not coercive in phi t. So the problem is that you get the task you have is to solve a minimization problem in which coerciveness fails. And coerciveness fails because of small values of epsilon. So in the limit, you are going to get oscillations for the solution. Okay? So this is not a good idea, in fact, from the numerical viewpoint. If you want to find a contour that makes y at capital T in norm less or equal, for example, that 10 to the power minus 10, something really very small, you are not going to solve the problem this way. Along the last years, there have been many people trying to get remedies to this. There have been several techniques to approach the problem by modifying the process. For example, via penalization, adding some terms to the function to minimize, or regularization, using high order time approximation. There have been many people trying to solve this problem and to get this way something really interesting. And none of them abandoned the idea of trying to find V with minimal norm. All of them tried to find this problem or something similar. Okay? There is an alternative that I'm going to present that is due to, well, we had introduced this alternative in collaboration with Arnaud Munch from Clermont-Ferrand. An alternative consists in using directly Kahneman estimates, weights that explode. Instead, look at this problem. Instead of trying to get the control V of minimal norming L2, imagine for a moment that rho is 0. Imagine for a moment that rho is 0. Then we try to find a weighted, we consider a weighted integral here with a weight rho naught that goes to infinity, and we try to minimize the integral of this quantity, okay? If we add rho that also explodes to infinity, we reinforce the idea, and we try to minimize this quantity. If we are able to minimize this quantity, then it is ensured that at the end, at capital T, we are not having oscillations, because Y is forced to vanish. This is ensured because of the presence of the weight, and also V. So we are going to get good controls and good states this way, okay? This is the alternative. So the task consists in proving that it is possible to solve this problem. This was done by Fulsikov, Ivanuvilov, and other people some years ago, and to find a good numerical method able to approximate properly this quantity, able to approximate this problem, okay? Let me say what can be done. This problem has certainly one and only one solution, exactly one solution, and the solution can be characterized with Lagrange theorem, Euler-Lagrange theorem, and the characterization says that Y, the solution to this problem, and V are given in terms, can be found in terms of an additional variable that is more or less the same than phi before, more or less. That is, that Y is equal to rho minus 2 times L star of P. L star of P is nothing but the adjoint operator of the heat equation, and V is essentially the restriction of P times rho naught to the power minus 2, restriction to little omega times 0t. So if we are able to find a variable P that solves a problem that I am going to write now, we will have Y and V by these relations. And the problem satisfied by P is this one. Let us take a look to this problem, because it is the key of the method, and it is the key, the most important idea that I am going to present now. This is a Lax-Milgrom problem, in fact. And you have here a bilinear form in P and phi, and you have here a linear form in phi, so it can be written this way. This is well posed, suitably posed in a space in which you have rho minus 2 L star P or square integrable. I mean rho minus 1 L star phi in L2, and at the same time this quantity also rho naught minus 2 P restricted to little omega integrable, okay? This is well posed in space capital P, in which all this is finite. Here we have in this space essentially the scalar product of P, nothing more. And we consider in P boundary conditions motivated by the presence of boundary conditions in the equations for phi, at x equal to 0, x equal to 1. So in this space, this is well defined, and it is a coercive bilinear form. In fact, it is the scalar product. So we are going to have a solution. We are going to have a solution if we prove, of course, if we prove that this is a linear continuous form on P. But this is a consequence of Cayley estimates. So what we have on the right-hand side, I will not present the details because it's not so important. Believe me, this is linear and continuous in P for this norm, okay? So we have a solution of this problem. So the computations are not here, but believe me that it's classical to deduce that the solution to this problem is given by these relations if P is the solution to this another problem. Okay? It is a technique that has been applied many times for many problems. We can, for a restricted, constrained minimization convex problem like the original one, we can characterize the solution, and the solution is given by this. The price is that, if you see here, this is in fact a second order operator. It is here also. So the fact is, in fact, this is the weak formulation of a fourth order operator, of a fourth order system. You see, usually we are accustomed to see something like the integral in omega of the gradient times the gradient. And you know that this corresponds to the weak formulation of a second order equation. Unfortunately, we have not here the gradient. We have the Laplacian, and here also. So when you integrate by parts, in order to get the formulation of the problem, when you integrate by parts, you are going to find fourth order derivatives for P, fourth order in space, and second order in time. If P is the solution to this problem, in fact, it is the weak solution of an equation in which you have, it is written here, second order derivatives in time and fourth order derivatives in space. Okay? This is the price we have to pay in order to do this. The good news, I repeat, is that we are going to get control V that is going to 0 exponentially at capital T, and this avoids the oscillations, the undecided oscillations that I have showed before, and a state that is going to go to 0 also exponentially. This is the good news. The bad news, there is always bad news if you have a good news. The bad news is that we have to solve a more complicated system because now we have second order in time derivatives and fourth order in space derivatives. Okay? If we are able to solve approximately numerically this system, we are done. We are done because in that case we'll have an approximation of P that will provide approximations of Y and B, and at the same time we have convergence results because we are not doing something strange. We are solving a Lax-Miller problem by approximating the space by a family of finite dimensional spaces. Okay? So a standard direct finite element approximation of P gives good results. The problem is that we have to use approximations of a kind that it's not usual because, I insist, the functions in P have first time and first order in time and second order in time derivatives in L2. So we need finite elements that are not Lagrange, are not the usual one. We need something more regular. Well, but we are going to do this. An alternative consists in mixed finite elements. This formulation can be rewritten in the mixed sense like something in which all the involved spaces only need one derivative in time and space. And this is a second possibility. I'm going to give some details now. So, standard finite element approximation, as I have said, of this problem needs a subspace in which we must have C1 in X and C0 in T finite elements. This is easy if n is equal to 1. For a one-dimensional problem, this is completely well understood. We only need polynomial functions, for example, of degree 3 in x, and of degree 1 in time. But for n greater or equal to 2, this is not trivial task. To construct C1 finite elements in space for n greater or equal to 2 is not easy. We have to work. We are doing things, but we have to work. And the good news, as I have said, is that if we work with spaces like this, we will have immediately a strong convergence of the approximations. This is ensured. Okay? The second possibility, as I have said, is you use a mixed reformulation of the Lax-Milgrom problem. This is well known in the case of the Stokes approximation. You rewrite the Stokes problem in the mixed sense, introducing the pressure, not forgetting the pressure, and then you approximate U and P. Well, this can be done also here. This can be done by introducing an additional variable, lambda, a multiplier. And in that case, if you integrate by parts and you rewrite this bilinear form appropriately, you only have first-order derivatives everywhere. So this is the second possibility. The second possibility is to approximate the mixed formulation of the problem. This only needs C0 finite elements in time and space, so it is okay. But there is a problem. The problem is that the strong convergence proof, to my knowledge, is missing here. I don't know how to prove that as h goes to 0, as the mesh becomes finer and finer, I don't know how to prove that this converges to the solution, to the original solution of the problem. There is a problem here because of the presence of the weights. So the theory is missing here for the moment. Anyway, we have been able to use this in order to get good results, good numerical results, as I have shown before. Okay. I come back now to the example that I shown before. This is solved by using a direct approach in which the approximation is constructed with finite elements on the mesh, finite elements that are polynomials of the third order in x, polynomials of the first order in time. And I use the tensorial product of these two spaces, and with this approximation, it works very well. Since it was a problem that only had one spatial variable in the formulation, it is easy. It's easy to construct this space, and it's easy to work with them, and the results are completely satisfactory. Okay. I'm going to finish with an extension of these techniques to a nonlinear problem. I think that it is still more interesting than what I have found before. There are several open questions related to this problem that, in my opinion, deserve some comments. This is a semilinear heat equation. A semilinear heat equation. I have put a coefficient here, but it is not important. But there is a semilinearity here. There is a nonlinear term, f. I am going to assume that f behaves like something that grows very weakly multiplied by s. This is what is called a weakly superlinear problem, because what we are considering here is something that goes to infinity like s multiplied by a logarithm. And I'm going to take p greater or equal to 1. So this is the situation. It is known that for p greater than 2, it is known that there exist functions f with f of 0 equal to 0, such that the system is not null controllable. This is an old result. For p greater than 2, this system is not null controllable. We cannot control, in general, starting from y naught and fixing the final time, capital T. And it is also known that for p less than 3/2, null controllability holds. So we can allow f to grow a little stronger than linearly if p is less than 3/2. And it is unknown what happens between 3/2 and 2. It is open. We believe that the problem is null controllable, also between 3/2 and 2, but there is no evidence. There is an evidence that it is not null controllable if instead of an equation, we look at the system. If we look at the system, there are more or less complicated arguments that show that the system is not null controllable. So we don't know. We are going to show, I'm going to show what happens to the problem when we take p equal to 1.4, I think. Something very close to 3.2. We are going to show that for these values of p equal to 1.4, we are still able to find v such that y capital T is equal to 0. And we are going to do this two ways. The first way is going to be what we have called fixed point iterates. Fixed point iterates means that we take z, we put z here, g is f over s, so we put z here, and we solve the problem. We solve the control problem. Once we get y, we again put z equal to y here, and we do it again. So fixed point iterates, classical fixed point iterates. It is open to prove that this converges, but there is a modification of the algorithm that gives conversions. So probably it is possible to prove that with the method that I have described, we get conversions. Anyway, numerically we get it. So numerically we get it, and as I have said, even when the power is near to 3/2. So this is going to be the first algorithm that I present. Very easy. We get yn plus 1 equal to lambda yn, where lambda yn gives the solution to this null control problem. Okay. Of course, this is linear, so to solve this problem, I use the arguments that I have presented before. So I write the null control problem as a Lax-Milgram system, and I solve the Lax-Milgram system. I approximate by a space in which we have C1 elements in X, etc., etc. And the second and more interesting viewpoint is this one. I use now least squares and gradient techniques in order to accelerate the convergence. This is done by considering again this problem and minimizing this quantity. If I minimize, of course, what we are looking here is a fixed point of lambda. A fixed point of lambda gives the result. So to get a fixed point of lambda, classical argument consists in reformulating the problem as a minimal in the sense of the least squares. In the sense of the least square, what we have to do is to minimize this quantity. This leads to the computation of a gradient of this quantity. It is technically a little bit more complicated, but it gives also good results. All this has been done, and we have, with these arguments, obtained what I'm going to show now. Okay, this is the mesh that I have used here. In this case, I have not, in order just to see what happens, I have used a mixed formulation for the linear problem. In the mixed formulation, as I have said, you don't have second-order derivatives. You only have spaces defined by first-order derivatives. So we can use Lagrange approximations. In this particular case, I have used P2 Lagrange approximations of the problem. That is only C0 and time and space. And I have solved this way the linear problem. And as you see, the function f has a bad sign. It tends to explode. And at the same time, the logarithm is to the power 1.4. So this is a weakly superlinear problem, but in bad conditions. Anyway, I'm going to show that we have been able to solve the control problem. Okay, this is the mesh, this is space, and this is time, and the control region is this one. This is the number of nodes, number of elements, etc. Some work has to be done. I have applied also a technique in which the triangulation, the mesh, is adapted to the results that I'm getting. This can be done with FreeFEM easily, and I have applied this technique just to simplify the computations. And you see that the final mesh has much less triangles and nodes than the initial one, because you know that, well, this can be seen that in this region, the solution, the control, and the states are practically zero. So we don't need so many triangles, so many elements here. Contrarily, we need a high number of triangles in this part of the domain, which is the part where variation is applied. Oh. The weight function is, it's not given here. No. The weight function is a function that has to be, is there? Ah, yeah. It is, this is the weight function that I have used here. It's not a unique possible weight function, but this is function. What has satisfied the weight function? It has to, this is the key. It has to be near a constant, with the derivative strictly, the absolute value of the derivative is strictly greater than 0 outside omega. Omega is this part. So what we need is that this is not constant outside omega. Sorry? Yes, the exponential. So rho is the exponential of beta over t minus t. So if t goes to capital T, so we have an exponential. Yeah. Does it make any problem here? No, because we are working with rho minus 1. We are all the time working, the weight that we use multiplied to v and multiplied to y is rho minus 1, rho minus 2. So in fact, what we use is a function that is near 0, near capital T. No, we don't have to work directly with this function, of course. Right? So this is the weight function. Thank you for the question, because it gives me the possibility to explain this. The important property of the weight function is to be a function whose derivative is different from 0 outside the control domain, because this gives the importance, this gives relevance to the terms in the Kahneman inequality. Okay? So I have used, as I have said, adapted mesh, and this is the final mesh that we find. This is the control. It can be seen here a little better. This is the control that we find. It's more or less complicated, but this is a control that starts to work just at time t equal to 0, because there are many things to do to control the system. And contrarily, near t equal to capital T, it is almost 0. And this is the state. This is the state, and this is a view, a three-dimensional view of the state. In this case, the state is not so simple as the state in the linear problem because of the non-linearities, of course. You have here oscillations that change. But again, near capital T, you have a state that goes exactly exponentially to 0. Okay? Well, I'm going to finish now with a list of references. I'm going to leave it here for you. A list, not exhaustive, but long list of references. These are general references on control of system governed by partial differential equations. There are classical books and more recent works. In particular, there is the book by Coron that is very interesting because it connects very well control concepts and nonlinearity. This is a continuation of the general references. If you want to deepen theoretical aspects of the things I have been telling you, there are several works. In particular, they give ways to solve many of, to attack many of the problems that have been presented. There are several works by Farid, Amarcocha, and others in which control of non-scalar systems is well described, and the results I have presented are proved. There is also a paper here. I have not spoken of it. A fundamental paper for the control of hyperbolic systems. I have not had time to speak of this, but this is very relevant. This is a continuation. You have here other results on the theoretical aspects. Okay. This is the work that I have been referencing about the most recent results on the Navier-Stokes, on the contrariety of the Navier-Stokes. If you change the boundary conditions, you can get things, as indicated there. And on numerical viewpoints, you also have a lot of works where different strategies are being applied in order to solve the problem, as I have said, apart from ours. These are the works that we have been done with Nomunch, in which these techniques have been applied. I finish with these references in which you can find some applications of control of PDEs to different sciences, and in the biomedical fields, and in particular topics related to cancer, etc. Okay? I think I'm going to finish here, and thank you very much.